Hello, this is Paul from Foresight Tech. The last lecture we discussed the area, how to find the area on the curve. In this lecture, we're going to discuss another classic problem in the history. It's going to estimate the distance if given the velocity. Okay. And the question is here. And for a linear motion, given discrete data points, we know a particle is moving in a straight line, but the velocity changes or the speed changes. Now the question is how to estimate the distance given two time points between two time points. So we say given the discrete point is this. If we know time t0, tiv, the velocity at ti, okay, and this is the discrete data points for the velocity, and so the distance between the beginning point t0 and the end point tn, what is the distance? I mean from t0 to tn, how long the particle moves, because the velocity changes. If we draw a graph, it look like this, okay, and I draw the graph for the velocity functions, of course, and the beginning is t0, the end is tn, and if the velocities go like this, we have the data is these time points, discrete time points. I mean t0, how high is the velocity, t1 at the time t1, how high, how fast is the particle moves, what is the vt2 or this, and this is the discrete time points. And one more, okay, so the increments may also be different. The increment means the distance between time points. That means t1 minus t0 is delta t1, delta t2, delta t3, delta ti. See, each time interval we have an increment. These increments probably are different. It's okay. So now the question is how to estimate from the time t0 to time tm, how long is the distance the particle travels. This is a classical problem in the history. So the classical strategy is here. Okay. And because the velocity changes, it's not easy to find the distance the particle moves. So we can do this approximation. We approximate the motion with the same velocity at each time interval. Means like the first interval t0 to t1, and the particle changes the velocity, but we can approximate as the velocity keep stable, no change, no change, no change in each interval. If the velocity no change, we know the velocity or the speed times the time is the distance, right? So each small interval we can find the distance, and then we add all the distance together, we find the total distance. We have basic two and strategies. So how to do approximation? Either use the velocities at the beginning of the time points, did the first. I mean we do this. So we're going to see the approximation, use a stable velocity. The first interval, use the velocity at the beginning which means t0, right? So it means do this, see, draw horizontal line, okay, and then I use this small horizontal line, the stable velocity, to approximate this curve. Use this horizontal line to approximate this curve, okay, in this way. And if we know this, so what is the velocity? If I write it here, so this time, in this time period, the stable velocity will goes to v at the left endpoint, right? So here at the beginning, the left endpoint, which is t0, okay. So I mean the first interval, so the first small interval, now we can find the approximation of the distance using the speed times the time increments delta t1, right? Okay, so now we can do this. I put it here. Now the distance, okay, put here. The distance, I use d to describe the distance, the total distance. Okay, can approximate by each small interval moves the distance together. The first is v at t0, right? This is the stable velocity times the time period, how long it goes, which means t1. The same, this is the first time period. For the second time period, use the beginning, which means the left. I can show this. Okay, so the second time period, the particle moves, we do approximation about the distance, which is v at t1, right, the left, times the time period, which means this, plus the second one is v at t1 times delta t2, and move on. Okay, I ignore others. So on the graph is do this. The third is do this approximation. And here I ignore the i's interval, we do this approximation, horizontal line. Okay, so here if I put is v at t2, everyone know v at t2 is the left endpoint. So this is the left endpoint, or the beginning is v at t I minus 1. So this, okay, it's probably similar, very similar. Okay, right? So this one is v at tm minus 1, the beginning. Okay, so this is approximation to the curve. This is step function, right? Everyone know we use step function to approximate the curve function of the velocity. So this time I finish this formula. This is the first distance, the second distance that goes to the last small interval goes distance, which is v at the velocity tm minus 1 times delta tm, right? Okay, so now let's look at a little. What is this? V is the height times delta t. Delta t is the width. The height times the width. This time exactly. This goes to here. If I highlight, what does this mean? This means exactly is the area, right? This is exactly is the area. So the second one is also the area of this rectangle. If we highlight the second distance is the second area, the third area, see? And now the questions exactly go back to the same as the area we discussed the last class. So here, the last. That means if we write what this exactly is the sum of all the areas, okay, or the rectangular areas. Means what? Means almost the same. You're going to find the area, right? We can use the area under the curve, the area of the rectangle to approximate what? To approximate the area under the curve. And if the approximation, if means n gets bigger or goes to infinity, and this approximation will definitely approach to the area under the curve. Means what? In this way I change. Okay, so I change. If, okay, so I put this. If all delta ti are the same, I go back to the very familiar formula. See, delta t1 equals delta t2 equals delta tn, all the same. This time we can change. If, okay, this is a if, right? If I put it here, and in this way, and then this distance we can change. So the first is v at t0. Delta t factored out, and then plus v at t1 plus all v at the last tn minus 1 times the final is delta t. So everyone look at this. Okay, so that's exactly is the formula for what? Is the formula of the ln, right? This is exactly ln. Means what? The ln is to approximate the area under the curve, right? So this is the left endpoint approximation of the area means what? And finally the distance is going to do this, is going to the area under the curve, right? Under the curve. See, this is very, very important, because when n gets bigger, ln approach to the area. That means the distance, now we can find the distance exactly is equal to the area under the curve. And the approximation, we can use the left endpoint, which means using the velocity at the beginning. So this is very, very important. See. Okay. So did the first. And the second is the same. It's almost the same now. You can see, right? Okay, so we find that the idea. This is the way how we can find the distance of the particles moves from t0 to tn by approximate. Okay, and finally the distance exactly equals to the area. The distance equals to the area. So the second is the same. Now, if we follow, we use the velocity at the end of the time. How to do? The first time period is here, time interval t0 to t1. It says use the velocity at the end, means we use this height to approximate. See? Okay, so this time. So what is the velocity? The stable velocity, we use this. Now how to describe this? This should be v at t1. That's what? That's a right endpoint. Right endpoint. The second, okay, I'm going to finish all this. This is the approximation, which means what? Which means v at t2 right endpoint. This is the stable function. Okay, so we have another stable function again. So this is a v at t3. Okay, and the ice interval should be like this. Okay, so what is this? Is a v at ti, right? The height. Okay, so this is step function. So this goes to the right endpoint of v at tm. Okay, now we do what? Do the same way. Okay, so vt1 times delta t1 is the area. That's the distance for the first interval. That's the distance for the second. That's the distance for the third. That's the distance for the ith. That's the distance. The approximated distance, of course, for the last. And we add all together is what? Is the area of the rectangular. Is all the sum of the rectangular area. And if I put it here, so in this way, is the same. Okay, d can approximate by the first is v at t1 times delta t1, right? Plus the second is v at t2 delta t2. The third, I ignore all, goes to the last, is v at tm times delta tn. So we know this is the sum of the area. And in special case, okay, in special case, if all the data are the same, which means what? We can put this v at t1 plus v at t2 plus all, okay, v tm delta t. That means what? If delta t are the same, see, in this way. Okay, so what is this? Is exactly the right. This is this, right? So if I put this is r n. What's that? This is a right endpoint. This is a right endpoint approximation for the area. Okay, that means the distance still use a right endpoint approximation. Okay, so can we see? So now the two questions, the two problems are the same problems. Okay, no matter is for the area or for distance, we always convert it to the area. And Isaac Newton developed this basic method, right? So to cut in pieces and add them together is the Riemann sum, and then take a limit, we go into the distance. Okay. And I have one example for you to do. Here's the example. Almost. So we look at the examples for this example. If we know the speed of a runner increase steadily during the first 3 seconds, and the speed is here. We look at it. T, the first row is the time point. The second row is the velocity, the speed that we found. And at the beginning is this is the second. Okay, so the time is 0, and the 0.5 seconds later, the velocity goes to 6.2 feet per second, and the increase, right? So the time goes to 1 second, and the speed goes to 10.8 feet per second, and moves on, and speed up, right? The runner speed up during the first 3 seconds. So of course the velocity changes is not a stable velocity, it's not a stable movement. So we have to use the method we just developed to find what to estimate the distance during the first 3 seconds. How far, okay, is the runner run during the first 3 seconds? Two questions. So this is the discrete data. The first is estimate the distance traveled during the first 3 seconds using the velocity. Okay, so look at it here. Using the velocity at the beginning. Okay. At the beginning means what? This left endpoint, right? So we should use the beginning is the left endpoint approximation. Okay, left endpoint. The second question is only a little bit of difference. We can approximate the distance by using the end of the time period as the staple. Remember, just the two. So the end, this is exactly the right endpoint approximate. Right endpoint. Now it's easy because we have a formula, right? We set up the timer. So if I put this is T0, okay, so 0.5 is T1, 1 second is T2, so this is 1.5 is T3, T4, T5, T7, right? Let me see. Yes, is T7. So we have this, and then we're going to do the calculation. And, we have 2.5, T0, T1, T2, T3, and T4. So I get it wrong. Okay, so T5. So it's here is T5. So here is T6 because I only have 3 seconds. Otherwise, it's wrong. And then we look at the increment. The increment delta T is the same this time. Okay, why? 0.5, 0.5, 0.5. Okay, it's 0.5 seconds. So this is the setup. Now we can use the formula, right? So the first 8. Now easy. We need to use the left endpoint, which means L. How many? 6. N equals 6, right? In here we can find out what is N. N equals 6. So is L 6 equals what? Remember the formula. Now I put the formula. Velocity function is V at the left endpoint, which is T0, right? Okay, plus V at T1 plus V at T2 plus V at T3. Okay, plus V at the last second. Okay, it's T5. This is only T. Well, I just wrote. We add T4. Okay, we add T5, and then times the T. Did the formula, then plug everything. See what we get. So the first is 0, and this is 6.2. We just put it one by one. So this is 10.8. What this is 14.9. What is 18.1. What is 19.4. Okay, what delta t is 0.5 times 0.5. Okay, it's very easy to do calculation. Use a calculator. What we get is 34.7 feet. Okay, so this is the estimated distance the runner run. Okay, goes away 34.7 feet during the first 3 seconds. So did the first. So look at the second questions. Change a little bit, use the right endpoint. So now is the same, right? Right endpoint is R6, and you know the formula a little bit different. Don't use this, use the second, because right. So is V at T1 plus V at T2 plus V at T3 plus V at T4 plus V at T5 plus the last V at T6. Okay, and the times delta t, and they plug everything in. So we added 6.2, right? 6.2, 10.8, 14.9, 18.1, 19.4, the last 20.2 times 0.5. Okay, do calculation. What's the answer? Or I find it's 44.8. This feet. Of course, the two estimates are different because we use different strategy. And this for these questions. And this for this lecture. Thank you.